Good
morning, class. My professor has sent me to deliver today's lecture. She's unavoidably absent, and she sends her regards. She asked me to inform you that next week, Wednesday, that should be 17 or so, that you may be having your second CA. And I think it's logical that we move very fast, because after this week, I don't know what the university calendar will say. Okay. In this class, we'll be looking at some work examples in which you are expected to note, work on them after the class. And when she's around on Thursday, she would shed more light. So this is an example saying that a 55 loop circular coil has a radius of 4 centimeters. It is oriented so that the field lines of the magnetic field are normal to the area of the coil. The magnetic field is varied so that B, that's magnetic field, increases from 0.2 Tesla to 0.45 Tesla in 2 milliseconds. Find the average induced EMF in the coil. So from the information, we said the loop is circular, you have a radius, its area you need to be able to get the area. And you can see that the magnetic field is changing. Have you done Faraday's law? Did you do Faraday's law in the last class? So if you are talking about Faraday's law, you should agree that for there to be induced EMF, there must be change in magnetic field. So some applications of electromagnetic induction: electric motors, electric generators, and transformers. For electric motors, we have electric motors in many applications. Our ceiling fan, they are made of electric motors. Anything that rotates around you, your CD player, your radio cassette player, they are made of electric motors, and they operate by the principle of electromagnetic induction. So let's look at this diagram that shows us what's in an electric motor. And when we're talking about an electric motor, we should conversant of two types. There is DC motor and also the AC motor. And when we say DC, I mean direct current. And I say AC, alternating current. The power that comes from NEPA, turn PHCN, turn DC is what? Direct alternating. I had direct alternating. So, but the major point is that when we say it is alternating, it is going up and coming down. And there is something we have ignored. Whenever you look at some electrical appliances, you see something like 50 hertz, a frequency of 50 hertz. Sometimes you see a frequency of 60 hertz. What that is telling you is that the power supply from NEPA is going from 0 to 220 volts, up and down 50 times in 1 second. That's what it's telling us. So that means when you are looking at a bulb connected directly to, let's say, tungsten lamp connected directly to the power supply. This is power supply from my BDC. What is happening there is that that bulb is coming up and going up 50 times in 1 second. Unfortunately, your eye is unable to detect that fluctuation. But if you visit our laboratory, we have some appliances, some equipment that can help you to visualize it, that it's actually going up and coming down 50 times in 1 second, going up and coming up 50 times in 1 second. The same thing applies to your computer screens. You see it saying 50 hertz. All those things are showing 50 times in a second, going up, coming up, going up, displaying many times. But your brain is not that sharp. Or sorry, if it's like our brains are not that sharp. I think it's better that way, right? Okay. So, looking at the diagram here, let me bring out a pointer. We have a North Pole and South Pole. So, we don't need much to say that the direction of magnetic field is from the left side of the screen to the right. So, if you look at the electric currents, you expect the electric current to flow from this battery, get to this point, and enter this coil A, B, C, D, and flow out. And since it's entering this coil, then you should agree with me that this is the direction of current flow, or if you like, point it to the opposite direction and say direction of electron flow. But at the end, you will agree with me that the direction of magnetic field will have a component that is perpendicular to the direction of current flow, and that should also give us another component that is perpendicular, which would be the direction of force. The direction of magnetic force should act upwards. So we should expect the direction of magnetic force to act upwards. So that these three lines that are these three arrows, the yellow, black, and green, should be neutrally perpendicular. So that will push this coil A to B, this line A to B, it will push it upwards. So when it pushes it upwards, because it's a force is acting in that direction, the force should cause motion. And when it pushes it upwards, what you have is push on. So when this A and B is pushed upwards, C and D should slide downwards. And when you look at these contacts here, that is, if you look at this ring, you'll see that there are two rings there, like two halves. So they call them split rings. So by the time the AB slides up, it will disconnect from the two rings, but it will still have some momentum that it will use to slide into the second ring. So in the ring, we have two halves of this ring. We have X and Y. So AB will slide out of X and move into Y. Then CD will now come and replace this AB. And what will happen again? It will receive electricity and continue to move in that direction and would have continuous motion. So at every particular point in time, current will always flow in this path through ring, semi-ring X into the coil in this direction, and it will cause a force, and it will induce a force that will cause this path to move upwards. So let's see if you can read through what is here. A rectangular coil of copper wire is placed between two poles of the magnetic field. Yes. A, B, and CD are perpendicular to the magnetic field. Yes. Two ends of the rectangular coils are connected to two split rings. Oh, sorry, they are P and Q. X and Y are brushes, but P and Q are the rings. So each of the split rings are connected to brushes. And these brushes are usually carbon brushes. So, and the axle is attached to the inner insulated parts of the split rings. External conducting edges of PQ brushes, two conducting brushes X and Y. So two conducting brushes X and Y are connected to the battery. So I hope the explanation is semi-straightforward. If it's not very straightforward, please find out time and look at it, read through them. So when the switch is closed, current enters the coil. So there is a switch here, K, and there is a switch K here. When it's closed, that is when current flows. When it's opened, there is no activity. So when the switch is closed, current enters the coil ABCD through X and leaves through Y. It enters through X and leaves through Y. The direction of the force following Fleming's left-hand rule. So following Fleming's left-hand rule, that's secondary school physics. Or do we have some first-timers hearing Fleming for the first time? Maybe we'll welcome you after the class. So force on AB pushes it downwards while CD pushes it upwards. So I think I've explained all this. The only thing there is grammar. So now, this is another work example. This is another example, not works. Another example that says calculate the induced EMF in a 150 cm square circular coil having 100 turns when the field strength B passing through the coil changes from 0 to 0.001 Tesla in 0.1 second at the constant rate. So fine, here we have area, we have number of turns, we have initial and final values of B within a certain time. So if we know the change that occurs within a specific time, then we can calculate the change. And it is that change that is very important for you to have magnetic force. If the magnetic field is stationary, then there'll be nothing special about it. So we'll see more examples about changes very soon. So still on electric motors, the current through the armature coil interacts with the magnetic field B to cause a torque tau. And that gives us this expression for torque. This is familiar, right? We've seen something like this before. The number of turns, the current flow, the area of the coil, magnetic field strength, and the angle between the coil and the magnetic field. So when the angle is 90 degrees, when theta is 90 degrees, we have the maximum torque. And when theta is 0, that means that they are parallel and the torque will be 0 because sine 0 is 0. Or let me say sine 0 degrees 0, sine 0, everything 0. So hence, theta is the angle between the field lines and the perpendicular that's perpendicular to the plane of the coil. A is area of the coil and N is the number of loops. So the torque always rotates the coil in the same direction. Therefore, the average torque is equal to, if you look at it, we have the torque, we find the torque to be NIAB. So, and the average torque is NIAB, ignoring the sine theta. So still on electric motor, there is something we call a back EMF in an induced coil. The back EMF opposes voltage source that drives the motor. When you, whatsoever you want to do in nature, there is always something that will say no. There is always an opposing force. If I say that, let's award all the students of physics 104, 40 marks in the CA. Some people will still say, no, why? After all I've read, let our skills be graded. There would always be some people that will oppose anything that is called change. It's part of nature. And even electric circuits, we also behave that way. When you try to send in electricity into an electric motor, there is one back EMF that will be trying to oppose that electricity from flowing freely. So that's part of nature. If you eat boiled unripe plantain, if you eat boiled unripe plantain, and you decide to swallow at some times, it gets stuck in your throat, right? It gets stuck that you even say, okay, don't go again, come out. It will still say no. There will be something that will say this plantain will not get to your stomach. And when you say no, come out, it will still say no. There is always something opposing progress. If you now say, oh, let me force it down, and you take water, you had it, you complicate issues. So there is always things like that in nature, and it doesn't exempt electromagnetics. So when we look at the net PD that causes current through the armature, so the net potential difference through the armature is the line voltage minus the back EMF. In short, when you switch off some electrical motors, or when you switch off electric motors, immediately that back EMF can be detected and can even damage appliances in some cases. So when we look at armature current is equal to the net potential difference. What is net potential difference here? Line voltage, that is the voltage supplied back EMF created by the coil. So the difference between them divided by the armature resistance gives us the armature current. And the mechanical power, which is, we know power to be equal to IP, right? So, and in this case, we'll be concerned with the armature current I and the back EMF V, if we are interested in mechanical power. So we're not just talking about just any current or just any voltage. We'll be interested in the armature currents and the back EMF if we are interested in mechanical power. I didn't say it. The power. Why not? We've said that the net potential difference across the armature is line voltage minus back EMF. And it is that net potential difference that helps us in determining the armature currents. So now, moving forward here, we are talking about mechanical power, just not any power, mechanical power. The mechanical power of the electric motor. The mechanical power of the electric motor. And the relationship between the mechanical power and current and voltage is product of armature currents and back EMF. So this is another example that it will work. So I suggest you go through these examples and work through them. Let me just read. In a motor, wow, time is running low. In a motor, a conductor. In a motor, a conductor. This is very confusing, you know. But let's be specific. In an electric motor, and this conductor is a conducting material, not your type of conductor. In a motor, a conductor that is 120 millimeter tall carries a current of 2 amperes. If it lies perpendicular to a uniform magnetic field of 1.4 Tesla, what is the force on the conductor? That's straightforward, right? No, that's straightforward. What torque is produced if the conductor is 50 millimeter from the axis of the motor and parallel to it? So we have 50 millimeter, this one dimension. We have 120 millimeter. If we need area, we know what to do. From the axis of the motor and parallel to it, and the field points from the axis to the Y. So please practice. Let me even see how much you have put in my mind. So this is another one that says a motor running at full load on a 118 volts line develops a back EMF of 107 volts and draws a current of 6 amperes through the armature. What is the mechanical power output of the motor? Disregarding frictional losses. And what is the armature resistance? So from this, we can determine armature resistance. We have one expression like that. This expression can help us do that. And we also have the back EMF, and we have the current through the armature. Then what else do we need? Then let's move on to electric generators. So when you take your electric motor is expected to take in electricity and begin to rotate and begin to turn. If you take that same appliance and you begin to turn it, somehow you will generate electricity. So it's like the same device. So there are machines that convert mechanical energy to electrical energy. And external energy source, such as a steam turbine, turns the armature of the magnetic field, the wires of the coil, cuts the field lines, and an EMF of it's epsilon, what was this? Equal to 2 pi NABF plus 2 pi FT. So in this example, such as a steam turbine, it can also be your petrol engine. The generators we have at home, they usually take petrol or diesel, and what they do is to create one motion, even including cars, to just make sure they start one rotary motion, and that is sufficient to turn the electric motor now, which we call alternator or dynamo, to turn an alternator or dynamo so that we would have electricity. So the mechanical energy from the petrol or diesel engine turns the dynamo or alternator and gives us electricity. Mechanical energy from the petrol engine now is taken by the alternator and now gives us electrical energy. And you should always remember that nothing is free in nature. If you calculate the chemical energy in that petrol, you discover that a lot of energy is lost when you use your generator. So, but that's not our business for today. Our business for today is to look at the relationship between those electric field and the magnetic field. So the number of turns in the loop, and there is nothing strange in this expression. The only thing that may be strange is F, and that is frequency. So when you take your alternator and you are so strong that you can turn it 50 times in 1 second, then you don't have to waste your money buying petrol. All you need is just to make it rotate 50 times in a second. And you'll be saving a whole lot of money. So now let's move on to what's in the generator. And you would observe that it's not the difference between what we have, the first diagram we had when we're talking about electric motors is a bit different from this, but I can even say they are the same. The first one we had is like a DC motor, and this one we are seeing now is an AC motor. This, in place of having split rings, and the first diagram, in this place we are having slip rings. So these, oh, okay, let me get it. So this, the wire on this side would always slip around this ring R1, while the wire coming from CD will always slip around ring R2. So it will be sliding in ring R2. Then you will agree with me that when current, okay, this is electric generator now. When you move this coil, this AB, when you move it upwards towards direction B, when you move it upwards towards direction B, you will have a current flowing away flowing away from us into the screen. But when it gets to this side, when the electric generator, when this armature is turned such that AB is now here, when it gets to this side, current will not flow away, it will flow towards us. And because it's flowing towards us, the direction will be said to have changed. And when the direction changes, that is an excuse for why we have a sine wave on and off 50 times in a second for IBEDC. Some other countries may prefer to use 60 Hz as their own standard, but Nigeria has adopted 50 Hz. So our appliances, they are usually designed to work with 50 Hz, and most devices even are adapted to work with a range of frequencies. So what we have here would, when this armature is turned, we will have an alternating voltage source. When it is not turning, when it is placed standing this way, the magnetic field that the coil will be experiencing will be constant. Hence, induced EMF will be zero. For you to have induced EMF, magnetic field must be changing. And a trick to have a change in magnetic field is for you to turn the armature around. So by turning the armature around, it will be experiencing variation in magnetic field. For the fact that it can experience variation in magnetic field, then electricity will be generated. Hence, current will be able to flow. So when you begin to turn this armature, EMF will be induced. By the time you power on your bulb, you will notice that the energy or the power you need to turn the armature will increase. And that is part of the opposition I was talking about earlier. By the time you power, let's take for instance our popular Tiger generators, you power it up, it's running, enjoying itself, you put on the fan, it starts to grumble. It's grumbling because it is experiencing an opposition to the free turning. It is experiencing something that's preventing it from turning freely. When you add another load, it experiences another opposition. So oppositions continue to build up as more current flows out. As current continues to flow out, there is more opposition, more back EMF, and that is why by the time you now put on the cooker or the pressing iron, then it will just tell you, bros, you're on your own. So what we have here, like I've said before, will give us alternating current. So for current to be induced in a coil or wire loop, the magnetic flux through the loop must vary with time. So magnetic flux through the loop must vary with time. So it's either you take your coil, you turn it around, or you take the magnet, you turn it around. You must just have a way of varying the magnetic field around the coil. That is why when you state Faraday's law, you say the rate of change of magnetic flux. You don't say magnetic flux. If you say magnetic flux, it is zero. No matter how large the magnetic flux, when it is not changing, you will have zero induced EMF. And if you state it that way, you will also have zero score. So for the energy generator, the inputs, mechanical energy is equal to outputs plus friction and its losses. So these are also one of the reasons why when we put something into one thing, we don't get it all out. These are like one of the, if you talk about it in Nigerian terms, these are the village people that will make it look as if you are not doing anything. And the village people, they vary from device to device, just like they vary from person to person. When you see some cars that have refused to retire, they use the same petrol like the recent ones, but instead of them to move forward, they don't just move forward, they make extra sound. Those sounds are not free. Petrol is paying. You ask it to move forward, it's moving forward, but it's also dancing as it's moving forward. Those dances, they are not free. Petrol is paying. This is another work example. This one looks like a work example. This looks like a work example. An AC generator produces an output voltage, and this is the voltage. Voltage equal to 150 sine 367 T volts. Where T is in second, what is the frequency of the AC voltage? So we have solution and hints that you may go through if you like. But when you say volts in an AC scenario, this is the voltage, is going up and coming down, going up and coming down. If we want to really define it very well, we should say this is like 0, it's going to 220, and it's coming down to minus 220, or let's even say 240. So it's going up, coming down. So at any particular, when NEPA, PHY104 IBDC, when they tell you it is 220 volts, fine. Let's just accept. But at every particular point in time, where if you agree that it is going up and coming down, then you should agree that the voltage is changing. It's not steady at 220 like they made us to believe. So at using this expression, at any particular point in time, you will have a certain voltage that is called the instantaneous voltage. The one that we have from NEPA that 20 is called the RMS voltage, which you may have seen or we will see later on. So the RMS voltage, we'll be talking about that later, or you may have spoken about it. But the major point is that if we say it is AC, it should have a voltage that is changing at every moment. But after every period, like you said from NEPA, it's 50 Hertz. When we say 50 Hertz, what is the period? That's 1/50 second, right? So 1/50 second, every 1/50 second, a complete cycle is made. And what you will have at 1/50, 2/50, 3/50 should be the same. If you move along this, our sine wave. So if you are the one that play with graphs and the likes, you will agree that year to year is one period. And when you move this your period, these two vertical lines, when you move them, okay, let me get a pointer. When you stay at this point and you move forward with one period, the instantaneous voltage here will be the same instantaneous voltage that way. So that's one of the beautiful things about sinusoidal Yes. So this is another work example. I can see something like solution here that says how fast must 100, not 100, 1,000 blue coil, each with 29 cents per area, turn in the Earth's magnetic field of 0.7 G to generate a voltage that has a maximum value of 0.5 volts. So it has int, it has solution. Let's move forward. Oh, so I think we can say we are through with this. Let's move to another slide. Good. So how much time do you have left? 15 minutes. And how much time do we have for lectures in the semester? Like 1 hour, 15 minutes. So let's go. Resistance in an AC circuit. So you've agreed. Even if you don't agree, I've not seen anybody oppose the fact that AC AC voltage sources are meant to move up and down, up and down, up and down. Even though you cannot see it, you believe it. And if you don't believe it, you're on your own. So an AC circuit contains AC voltage source, like a small generator. Our batteries are DC voltages. And one more element. So in this case now, we are talking about where we have an AC source, and the voltage of the AC source is V naught, V equal to V naught sine 2 pi ft. So it's connected across a resistor, and the current flow through that resistor is I. The resistor is having a value R, and the current flow through resistor R is I equal to I naught sine 2 pi ft. What is V naught? What is V? What is I naught? What is I? Let's start with V. V is the voltage, instantaneous voltage at every particular point in time, while V naught is the peak voltage. So when we think about the AC to be something like this, going up and coming down, the height here is V naught, and this place to this place is one period, 1 over period, or we call it wavelength. The time taken to make a wavelength is 1 period, and the number of wavelengths you can have in a second is a frequency. So also, since the voltage is flowing, the voltage is across a resistor, current is flowing, and that current is also of this nature. Oh my, let me take this back. Just have to manage this one like this. So the blue line here is the current, and the height of this blue wave is the amplitude, and that amplitude is the peak current, and that is I naught. I naught is the peak current you can have. So when you have a sine wave, one of the things you get to know is what is the amplitude and what is the frequency. So it's easy for us to relate the alternating voltage source to give us a sine wave And one important point to note is that when the alternating voltage source is connected across the resistor, the current and the voltage will be at the same phase. What that means is that as voltage is increasing, current will be increasing. And as voltage is decreasing, current will be decreasing. So they will be moving together. When voltage is zero, current will be zero. Voltage is negative, current will be negative. So they will always move together. When we get to some other circuits that has to do with capacitors and inductors, the current and the voltage will not move together. So, still on resistance in the circuits, 2 pi f, you must have seen 2 pi f, or 2 pi f being defined as angular frequency in the past. So that's the only strange thing I see here. So the W here is the Greek letter omega, is the angular frequency of the voltage, and it's measured in radians per second, and it's related to the frequency by 2 pi. So there's nothing new here. Resistance in the circuits. So when we say Ohm's law is V is equal to IR, and when we think about I, then we are talking about V over R. So when we know instantaneous voltage to be V naught sine 2 pi ft, dividing it by R will give us I. So V naught divided by R should give us I naught. So that is why we have this. So okay, so what I've just said is here. V I naught is equal to V naught divided by R. I was thinking I will see something like transformers along the line, but I don't. There is one point I wanted to note, thinking I'll get to transformer. Let me just chip it in before we go too far. You must have heard about transformers. Or have you done transformer? You've done it in that class. Yes, no, yes. So at least the transformer has two coils, the primary coil, the secondary coil. When you put voltage in the primary coil of the transformer, you get an output voltage, right? You see, that voltage you put in must be an alternating voltage. If you put a direct voltage there, you will not have a steady output, because the transformer operates based on the rates of change of magnetic flux. So when you put in alternating currents, the current through the primary coil is changing, then flux, magnetic flux is changing. And is that changing magnetic flux that will induce EMF in the secondary coil? If you take your battery and connect it across a transformer, as you are connecting, you will see an output and it will fade away. And there will be no output. And when you disconnect, you will see another output and it will fade away. So if you want to use your battery with a transformer, you need to be connecting and disconnecting, connecting and disconnecting all around, non-stop. So that is why we have inverters that will make sure that it's doing something like connecting the battery to the transformer and disconnecting it all along and on. So let's come back to this circuit. I've drawn a circuit diagram that looks like this. And what this is just showing us to say that we have a voltage source B of this nature, of this faded line. We also, then, if it's connected across the resistor, we will have the currents represented in this one. So, I think spoken about this. How many minutes do we have? Okay, oh. So when you look at the currents, or let's you look at the voltage source from an AC source, we said it goes, it alternates from the positive and the negative. Positive and negative. If you are asked to perform the normal straightforward integration, where you are asked to find the area under this graph from this point to this point, you are asked to find the area under the graph, your answer would be 0, because the area here is equal to the area here. This is like a positive area, this is like a negative area. You see 0. But something in your church mind is telling you it shouldn't be 0. This thing is doing work. It doesn't make sense for you to call it 0. So when we are talking about power, it seems like it sounded like a pastor. We're talking about power, electric power. I square R. Like, okay, this is the only formula I have in my head. When you talk about power, power is equal to IV. And the other formula I have in my head is to say that Ohm's law, B is equal to IR. So this P is equal to Y squared R is something I derive when at it. Because how can I be putting many things in my head and see that I squared R? So, no, there's nothing else to like that. So when you decide to have the square of current and the square of voltage, when you said what is the square of the current, you can easily do, say, I square and say I naught square sine square 2 pi ft. When you do that, it's easy for us to say that I square, that is I square, is equal to half I naught square. And this I naught, we know it to be the instantaneous, peak current, peak current. Why I is instantaneous current. So from this expression, we can come to say that then what is I? What is I? That I will be the square root of both sides, right? And it will not just be the square root of both sides, it will be I RMS. Root means square. Root means square. You square it, you average it, and you root it. Then that is what has been done. So if you read through this place, you will see that some averaging has been done, and at the long run, what we have here is I naught divided by root 2. So for a sinusoidal alternating voltage source, I RMS is I naught over root 2, and V RMS is peak voltage over root 2. So resistance, so root 2, well, we say I naught divided by root 2. Some people that like to play with mathematics will say it's the same thing when you go to solve. You say I naught multiply the numerator and denominator by root 2. We have I naught root 2 divided by 2. So it's still the same thing, just playing with figures. 1 divided by root 2 is 0.7071. Root 2 is 1.414. So when you say 1 divided by 1.414 is 0.707. So it's easy for us to now say that IRMS or VRMS is equal to 0.707 times the peak current. And now it's now easy for us to say that to now define our power. To say that power is equal to the product, the I square R we had initially has now been properly defined to mean that the square of root mean square current and the resistance in the circuit. So P, which is I square R in our DC circuit for AC circuits, it's not just ordinary I, but the root mean square current. And when we say VRMS, the root mean square voltage, it will mean that if, for instance, let's take NEPA, for instance, they say they supply us with 220 volts. That 220 volts is the root mean square voltage. If we plot the sinusoidal waveform coming from NEPA, it will go above 220 volts. The waveform, the peak we should have will be IRMS times root 2. So IRMS, which is 20 volts, times root 2 should be the peak voltage here that we'll call the V naught. The peak voltage that we call the V naught is 220 volts times 220 volts. But the reason why we talk about this 220 volts so much is that when you connect a 220 volts battery, DC battery, when you connect it to an heater, it will work as perfectly or as similarly to what the power from NEPA would give you when you connect that their sinusoidal voltage, whose peak is 220 times 1.414. Because so 220 times 1.414, what's that anyway? That should be 3 something or something. Yeah. 3 what? 311. So if it goes as high as 311 volts and comes down as low as minus 311, up and down that way, but at the long run, what you have that you recognize as the voltage, presentable voltage, VRMS, is 220 volts. So this, so that's 311 that's going up and coming down across 311 will eat up a coil as if you have connected a 220 volts battery or 220 volts DC source across that heater. So if this is plotting power with time, so average power is the peak power divided by 2. I think you can just read through these ones, they are straightforward. I've spoken about this as well. VRMS is the same as V naught over root 2, just like we did to current. And VRMS is IRMS times R, just like we have V naught to be equal to I naught times R. So going through this page will also, there is nothing strange there. So the resistance and the AC circuit, we've spoken about this before. And a lamp of 60 watts, so this is an exercise, a lamp of 60 watts is plugged into a 120 volt outlet. What is the RMS and peak current through the lamp? So since it's 220 volts outlet, the RMS is 120 volts. This is a 120 volts outlet, the RMS is 120 volts. And the peak voltage is 120 times root 2. And easily, since we know power, we know voltage, we can determine resistance from power equal to, I think, V square over R. So I think by the time you meet on Thursday, if you like, you start all over again. If you like, you do work examples. So I wish you the best in your examinations, to see and the exam. So for those that failed it, I was asked to tell you that the second CA will be coming next week Wednesday, which is 17th of May. So more information will be passed across to you.